Hey folks, today's talk will be about software design principles, and I will try to make a case to you of why you should care. First, a little bit of know your speaker. I'm Dimitrios, I come from Greece, and I'm based in Amsterdam, the Netherlands, but also in Athens, Greece. And yes, I'm trying to manage a double life. I've been involved with software for the last 13 years or so, primarily with web applications, and have worn multiple hats, from backend engineer, front-end engineer, architect, tech lead, engineering manager, even CTO. But my passion really is software design and architecture. Let me introduce you to design types. Just like personality types that most of you are probably aware of, there are also design types that describe how you usually go about designing software. I've recently stumbled upon this great website that can tell you what your design type is by answering a simple questionnaire. You can find your own type at designtypes.net. And I'm not affiliated in any way, right? It's just a great website to check out. So my design type is the author. What does it mean? It means I like to design software just like an author is writing a book. The story is carefully planned, easy to read, with elegant and creative machinations. And as such, I advocate for simple and easy to understand solutions, always keeping the bigger picture in mind, and I try to find the most elegant solution for a given problem. I also use technology as a tool to solve my problems, which means I'm not afraid to use different programming languages, frameworks, and whatnot, if they're better suited for a particular problem. All right, let me tell you about Zawinski's law, and which is one of the main reasons we're having this talk today. So Jamie Zawinski, commonly known as JWZ, is an American engineer who is best known for his role in the creation of Netscape Navigator, Netscape Mail, and even Mozilla.org. Zawinski once said that every program attempts to expand until it can read mail. Those programs which cannot expand are replaced by ones which can. What does he mean? Zawinski really described the desire of every software to grow and become a platform. For example, an app that displays hypertext documents starts reading email, then it becomes an OS. A text editor becomes an IDE, and then becomes an OS. So Zawinski laws is all about software growth, which is inevitable. To guide and control that growth before it consumes us all, we need a set of principles. Therefore, I will talk to you about the most important principles that have been guiding my software design decisions, which I have found that result in good software no matter its size. These principles are obviously not mine, but rather come from the work of a very brilliant people such as Andrew Hunt and Evan Thomas from the Pragmatic Programmer book, General Responsibility Assignment Software Partners from Craig Larman, Robert C. Martin, Uncle Bob, and many others. All right, keep it simple, stupid. I'm confident you've heard or read about this many, many times. Yet I feel it has to be mentioned again and again because it's important, if not the most important of all the principles out there. Keeping it simple and avoiding unnecessary complexity always results in faster development, easier to understand software that yields fewer faults. For the history, KEYS was coined by Kelly Johnson, lead engineer at Lockheed Skunkworks, on 1960. However, we can find mentions of this principle even earlier. For example, in Leonardo da Vinci's quote, "Simplicity is the ultimate sophistication." But what is simple? And how much simple? Those are all valid questions because simple is subjective. What I consider simple might be different from what you consider simple. Imagine you're sending me a pull request and I comment on a code block that needs to be simplified. But you already thought it was simple when you created it in the first place, right? So we need a way to come to an agreement, a shared understanding of what simple means for both of us. How to do that? Well, we can find some guidance if we look at how a dictionary defines simple. So simple is defined as something that is easily understood, composed of a single element, or when talking about items, something that is basic, uncomplicated, without much decoration or ornamentation. This definition helps a bit, but probably not as much as we would like to. So how about we look at how the opposite of simple is defined? If we can clearly distinguish what is not simple, we have way more chances to identify simple, right? And the opposite of simple is, of course, complex. So complex is defined as something that consists of many different connected parts, often in a complicated way. Now, if we combine both definitions, we could at minimum agree that simple is something that is easily understood and does not consist of many different connected parts. Okay, now, if we want to attempt to avoid complexity, we must first understand where complexity comes from. There are multiple sources of complexity in software, and from the list that I have here, you will probably notice that you might be able to avoid some, but only mitigate others. For example, a business process can be very complex. The software that implements such a process will inevitably be complex as well. This complexity can only be mitigated but never removed completely. Unless, of course, you have a magic wand that makes everything simple, please reach out to me later. We also have complexity that originates from Conway's law, or in other words, the organization itself. So Conway's law describes the effect an organization structure and communication lines have to the software that leads to additional complexity. So broken communication lines, suboptimal ownership boundaries will always lead into complexity in the software because you need to account for them. Then you have complexity that is coming from us, the engineers, right? You might have noticed that the listed items that I have here are mostly well-known patterns. For example, premature optimization, it's the root of all evils, right? You're not gonna need it, but you're still gonna build it. Adding more and more code without really adding value, yes, effectively gold plating the software. And your most favorite tool, the golden hammer, right? Because if all you have is a hammer, everything looks like a nail. This is very common when we are familiar with limited set of tools, and then we use the wrong tools to solve a simple problem, which results to more complexity. And of course, there is magic, right? And it probably doesn't need much explanation, but if you end up saying, I don't understand any of this, it works, but it looks like magic, then you've spotted the pattern. Don't let your engineer ego generate magic, right? We don't need to outsmart our fellow engineers. A highly complicated solution for a simple problem might look clever, but it will be a pain to work with. All right, now let's look how we can tackle complexity. For the complexity that comes from the business requirements, you must first make sure you clearly understand the goal and the value that is to be gained. Work together with your product folks because you are in the same team. As long as you both understand the goal, you will be able to have a healthy discussion and arrive in a solution that can best achieve it in the simplest way possible. Often, the value of a more complex process really does not justify the cost. The gains, in the long run, might turn into more losses. So challenge the goal, come up with alternative, simpler approaches. Use data and not gut feeling to make an informed decision on that. For complexity that comes from the organization, it's usually difficult to avoid, but it's not impossible. So challenge the status quo, remove the communication barriers. Because you're doing things in one way today, doesn't mean that this is the best way to do things. Change your mentality from this is another team's problem into what can I do to help my team and that team achieve the goal that we both have to achieve. Work together and assume more ownership. For the complexity of the code, now that you know about the anti-patterns that I've shown you, learn how to recognize them and avoid them. Simple, right? Also, use the right tool for the job. Nowadays, there are hundreds of tools at our disposal to solve the same problems. Some tools do it better than others because that's exactly why they were created for. Some organizations are afraid to use different tools, and this might be because of lack of awareness or experience from the engineers themselves, right? Because we are humans, and humans are known to be afraid of the unknown. But with all the available documentation, actual examples of teams using those technologies in production, you can't really say it's unknown anymore. Advocate for best practices, but most importantly, agree on them with your team in writing. After that, on each peer review, you can refer to them and ensure that every new code adheres to the principles you have adopted. Lastly, remember those decisions that were made much time ago, maybe before you even joined the organization, right? And if you're unlucky, which happens very, very often, you don't even have documentation or a decision record about that decision. Well, turns out that the forces that drove those decisions back then might not apply anymore today, right? Business requirements might have changed, the tools themselves have evolved. So what you can do is periodically review those decisions, and if the forces are different, update them. Simple. In the end, what we do as engineers every day is trade a problem for a different problem we're more comfortable dealing with, right? Use the KISS principle to guide you in trading for a simpler problem and make good deals. All right, KISS is a general principle that is not limited to software. Now, let's talk about the principle we can only use within software, the model principle. The model principle states the object structure of the software should model and mirror the concepts of the real world it supports. The principle originates from the roots of object-oriented programming, where objects are designed such as to simulate the behavior of a real or even imaginary world. And even though you could argue that object-oriented programming also introduced a lot of issues, and this is true, the principle itself is still a very good principle to have and provides tremendous value. In practice, how you would see that principle applied is that if you talk about products, shopping carts, invoices, orders, and whatnot in your business, you should have the exact same models in your software with the exact same names. Moreover, the actions defined on those objects should mirror the real-world actions. So, for example, if a user can change their password, you should have a change password action in your user model instead of a generic setter like set password. But why should you use the model principle? Well, the most important reason is it significantly reduces cognitive load. To work on a problem domain, you need to inevitably understand it. If the software structure does not match the problem domain, you now have to learn both the problem domain and the software structure. Then, using the same language in the real world and in the software world, you achieve a shared understanding with technical and non-technical people alike. Finding a solution, implementing a business process, and making a decision together with a group becomes so much easier. Lastly, it simplifies the software structure. It's easier to understand where some functionality should live and separate the responsibilities or even argue if that functionality is needed at all. Applying the model principle will help adopt a common vocabulary that will be shared by product folks, engineers, and technical or non-technical stakeholders alike. This common vocabulary is discussed extensively in the Blue Book, if you know the domain-driven design by Eric Evans, under the name of ubiquitous language. For me, if you are to take only a few learnings from that book and disregard all others, right? Those would be the concept of ubiquitous language and the domain events, which is a topic for another talk. Ubiquitous language will improve communication, allow for effective discussions, and create a shared understanding within the team. No longer you will be lost in translation, where a product owner talks about a shopping cart, but your software calls this class a thing, like literally a thing. So good luck trying to onboard other engineers on the concept of the thing and explain what you can do with that, while at the same time explaining to them how it represents and models the business domain. Here is also the right place to mention the old great comment left by an unknown engineer. When I wrote this code, God and I knew what I was doing. Now God only knows. Just because you might have designed a product or an invoice class in your software, it doesn't necessarily mean that you're fully applying the model principle. In fact, it happens more often than not to apply the principle only partially, leading to a very common anti-patterns that are easy to spot. The far more common anti-pattern is the anemic domain model. You can spot this anti-pattern by looking at entities that have lots of getters and setters, but they don't enforce any business rule. As a result, entities become just data holders. So where do the business rules live then? Who protects them? Who enforces them? Well, you will most probably find them polluting the service layer, which will now not only be responsible for coordinating the domain layer to perform a business process, but also now has to enforce the business rules that belong to the domain. In the end, the service layer becomes very similar to a transaction script, which is another common anti-pattern, a long series of procedural calls. So on the right side of the slide, you can see how the anemic domain model could look like on an invoice entity, where the business rules are checked outside of the entity itself and live into something service. If we fully apply the model principle, we will arrive to the rich domain model pattern. We can see that the business intent is now clearly represented in the invoice object with a clear action named pay, right? Now the model itself can enforce the business rule of being paid because it has all the knowledge about that rule, and it's the only one that can naturally do this. It is the only one that knows how to check if it hasn't been paid before. And it can also have other business rule or behavior, for example, allowing partial payments. The service layer is simplified and restored to its only responsibility, which is coordination. Let's look at another scenario where model principle help us create better software. Typically, a web application accepts HTTP requests, but more often than not, it might also expose a CLI port. In both cases, it parses some input parameters given by the user, it will validate them and pass them on deeper to the application to execute the business case. It's easy to see that the input validation can, and many times you will find that, is duplicated in each of the ports. It's also easy to see that storing the input as primitives is an invitation for logic errors. Looking only at the distance variable, you can tell whether the value is in miles or kilometers. You always need another variable, which is the unit, right, to specify this. In addition, the value of those variables might be altered throughout the program, and there is no way you can guarantee or protect them from this happening. What you see here is basically the primitive obsession anti-pattern, the urge to store everything as primitives. On the right side of the slide, you can see how the model principle solves this problem by using value objects pattern. Value objects are simple data structure. They look similar to entities, but they have no identity and are immutable and defined by their values. So if you look at the distance class, it's easy to see how simple and powerful this concept is. First of all validations live inside that class. They are in the place that they naturally belong, and they're not scattered anymore or even duplicated in different parts of your system. Second, you can't create a distance object unless it has passed its own validation. So as long as it's created, you always know in your software that you are working with a valid distance, right? And it's immutable. It's created once, and it cannot be changed later by anyone because, as you can see, it does not expose any setters or any behavior to change something. Lastly, the object can also expose other methods to make it easier to work with. For example, it can expose methods for converting the distance into miles or kilometers, serialize it to some format, a string, I don't know, JSON maybe, right? And possibilities are endless. And with that, we've concluded the talk about the software, about the model principle. Let me introduce you to my all-time favorite principle, the information expert principle. It's a principle that can guide not only software design decisions, but even organization structure decisions and more. This principle originates from the work of Craig Larman, applying UML and patterns, part of general responsibility assignment software patterns. The principle is simple, but very, very powerful. You should not ask for information from an object or at the systems level a service. Do some work with that information and then update the object or the service. The one that has most of the required information should be the one responsible to do that work. There is no better way to explain that principle than a concrete example. So, to make the symptoms even more clear, I will use an example at the systems level rather than a module class level. So here we have a system context diagram using a C4 model that describes at a high level a simple accounting platform. At the top, you will find the two main user types for this system, the business owner, who is using the platform to send invoices to their clients, and the client of that business owner who wants to pay the invoices using the platform. In the middle, you see the accounting platform, which is composed of a user interface. Usually this would be a web or mobile application even, and some backend services that provide the business functionality. Lastly, you will notice an external to the platform service, the payments gateway, that is responsible for the actual payment processing. For example, it could be like something like PayPal or Stripe. Let's have a closer look on how the pay for an invoice use case could look like using a sequence diagram. So the client wants to pay for an invoice with ID 123, talks to the user interface. The user interface will then talk to the payment service and say, hey, someone wants to pay for invoice 123. The payment service then will talk to the invoices service, get the invoice 123, right? Then start validating some rules. For example, if invoice is already paid, right? If the currency matches, and maybe some other checks. After this has happened and is successful, the payment service will use the payments gateway to actually process the payment. It will record some internal state, and when this is done, it will talk again to the invoices service, mark the invoice as paid, and then probably process some other side effects after a successful payment. The first thing you will notice is the increased amount of service call, right? So payment service has to talk to the invoices service twice. Now, if the service is leaving the cloud, this means network calls, which translate to possible failure points, right? The biggest mistake an engineer can do is assume that the network is reliable, and it is not. Second, you will notice consistency issues, right? When the invoice is retrieved from the invoices services here, Until it's marked as paid, anything can happen. There is a network latency. For example, there is at least, I don't know, 2 milliseconds latency, right, between each network request. Then you have to process the payment, do some calculations, whatnot. There are delays in between. And by the time that you actually want to mark the invoice as paid, if all the other stuff have happened, the invoice might have even been deleted, right? And what happens there? Well, this is a very, very bad user experience for the client because they didn't, change anything. Maybe the invoice was deleted by the the business owner, right? So there, like they started a process and then they got a bad user experience in the end from our services. Also, you might need to do some compensation. There might be race conditions, even like multiple payments going on. There is a lot of things that can go wrong there. And apart from that, there is high coupling. And although I put that point as last, it is actually the most important issue that we have here, is the strong dependencies. So high coupling means that the payment service needs to know about invoices. And the way it actually knows about that, because it needs to talk to it, is that it needs to implement a client or so. It needs to know about this API, the protocol. It probably needs to implement an anti-corruption layer, probably some circuit breakers, handle the faults of the communication and whatnot. So you see now, payment service becomes very complicated. It also validates business rules that actually belong to the invoice service, right? You basically see the anti-partner that we talked before, the anemic domain model, but now on a services level. For example, if someone changes the business rule, right? If like the invoices service, which is probably maintained by a different team, right? Changes the rules that the invoice can be paid. Now both services need to change. Imagine now the effect that this has to the roadmaps of both teams. These are problems that the information expert principle can solve. So let's look how this can happen. If we were to apply the information expert principle, we would first ask, who knows that the invoice can be paid? And here I'm talking about the capability of the invoice being payable, right? This is a decision or a business requirement that is taken in the invoices service, right? Probably the product owner that is working the team says, oh, invoices can be payable. Let's build functionality to allow that. So the next thing we would also ask is, who knows whether the invoice has already been paid? Well, again, we talked about that, right? It's the invoices service that knows whether this state change on the invoice has already happened. Also about other rules, right? Where who knows whether the invoice should be paid only on the same currency. These are all business rules that belong to the invoices service or the invoices domain. So let's now invert the relationship and actually have this process start from the invoices service. So the client wants to pay for an invoice 1, 2, 3. The user interface now will talk to the invoices service first. Well, the invoices service will get the invoice from their database because it's their own database. It has their own, it's a local database. It will validate any kind of business rules the invoices service has, right? Because they own those rules and they can validate them. They can enforce them even. Then, if all goes well, it will talk to the payment service to actually do the payment processing. Payment service will do its own thing, will talk to whoever other service needs to talk to, keep some state. And when this is done, right, the invoices service will mark its entity, right, the invoice as paid, and then start processing other side effects, which could be anything, right? Could be sending some events to other services to be consumed by other services. It doesn't really matter here. What you see now is that the immediate gain, right? So the network calls between the invoice service and the payment service now are reduced to 1 only. That's it. Second, we remove the consistency issues, right? Because we start from the invoice service, since it has all the information to start that action, right? We know whether the invoice is already paid. It has its own local database. It's the one that controls that consistency boundary. It can also, validate all the rules. So in the end, you remove completely the consistency issues. There is no need for, there are no race conditions anymore because the invoices service can handle that. And there is no need for any compensation work. And the most important thing, right? There is now low coupling between the services. Why? because the invoices service at the start is the one that said, you know what, my invoices need to be payable. So it's the one responsible for talking to any kind of payments, let's say processing service. So it's the one that will have to build that communication, and the client, of course. The relationship here is embedded, right? Instead of payment services talking to invoices, we see invoices talking to payments. But now that means that payment service is simplified. It only talks to the external payments gateway, and it keeps its own state. It does not need to know about the concept of invoices at all. It does not need to check any business rule of a different domain, right? And it can also now be reused by other, let's say, services. If, for example, now you would like to introduce, I don't know, something else that can be payable, they can use now naturally the payment service, talk to it to process the payment. So as you can see, transaction is simplified, consistency is achieved, coupling is reduced, and the engineering teams live happily ever after, probably. Time to talk about the principle of least astonishment, also known as the principle of least surprise. And I believe a reference to Geralt of the Witcher is justified here, due to him, if you know the series or the game or the books, due to him invoking the law of surprise and getting a child surprise. All right, this is a well-known principle that is mentioned in The Art of Unix Programming by Eric Raymond, but you can also find a reference to it in the Tao of Programming book by Geoffrey James. It is based on the fact that the easiest programs to use are the ones that demand the least new learnings from the user. Surprises lead to frustration. Surprises from software is also something that nobody likes. When the user of an interface, be it a user interface or a module interface, is surprised, they will get frustrated and they will try to figure out in many ways how to get the system to do what they wanted, what it should be doing in the first place. This will lead to even more frustration and even mistakes, right? Because of misuse. And the effectiveness of the user is greatly reduced and the impact. Again, the principle is best explained using an example. And what best example there is than the JavaScript language itself? I'm borrowing these examples now from the great lightning talk of Gary Bernard on CodeMass 2012, which I recommend you watching if you haven't already. So let's look what adding two arrays in JavaScript, what we would expect to return, right? Would it be an error? Would it be an empty array? Well, none of the above. It's an empty string. Let's see what an empty array and an empty object in JavaScript would return, right? What would you expect here? An error, possibly, because we're talking about different data structures anyway, right? Array and object. Interestingly enough, it's a string of object. Yes. Another example. What if we are to reverse the order of the summing parts? So let's say if we want to add the empty object first and then the empty array. What would you expect in that case? I would say we shouldn't be surprised, right? Because we just know this is a well-known property in mathematics. It's called the commutative property. So like it should be no surprise. We should get again string object object, even though that doesn't make much sense. However, you will find out it returns 0. And I know you're baffled now and you say, what the hell is happening? So let me tell you what is happening here. And what you just saw is basically the principle of least surprise, actually the opposite of the principle of least surprise in action. So what is happening under the hood in JavaScript, right? So the addition operator in JavaScript works only with numbers and strings. You can use it, however, to add any kind of values. So JavaScript under the hood will try to convert those complex values into their primitives and the primitives into a number or a string. Therefore, let's look at the first case, right? An empty array is converted to an empty string. That is simple. So if you add two empty strings, then they will give you an empty string as a result. So that is now kind of explained. Now what happens in the second case, right? We have an empty array, which is an empty string, and then we have an empty object. Now, an empty object internally is converted into the string object object. Yes, this is what is happening internally in JavaScript. So basically you have empty string plus the string empty object object, and then you get the string object object. So now this should be a little bit clearer what is happening in JavaScript. But the most surprising thing is the last example, where you have an empty object and empty array, and then you get 0 and you say, okay, what is happening? So interestingly enough, JavaScript will see the empty object that we think it's an empty object here. However, for JavaScript, because it comes first in the expression, JavaScript interprets it as the empty code block. So it ignores it completely. Then what is left is an empty array, as you see here, that we know it's an empty string, and the plus operator. However, in this case, because the operator comes first, like there is nothing else, the JavaScript has ignored the empty code block. It is not the plus operator anymore, there is an operator, but is rather the unary operator that is converting any string into a number. So basically, you take an empty string with a unary operator at the start, it's converted to 0, and this is how it is all explained. All right, let's have a look at some other surprises. How about misleading names, right? Here we look at the function, the add user, that it says it's adding a user, but doesn't really do it, right? It just returns a new instance of the user. So did we, no, if we look at that function without seeing it being used, or actually, sorry, if you look at it where it's used, then you would say, did it add a user here? What is actually happening? It's confusing and it's surprising. How about unexpected side effects, right? So you call a method probably somewhere that you do some bulk processing, right? Only to find out later on that you have emailed the whole world. Fun times in production, true story. Then we have inconsistent return types, right? So you call a function, you expect to get a user instance, but sometimes you might get a string. So now the caller needs to have mechanisms and if and branches to handle those cases. Not a good experience for the one that consumes that function. Then let's look at the surprises at the user interfaces, right? So misuse of specifications. Imagine a happy user of your API that sends you a request. Something goes wrong here, and then you respond to them with an error 400. Right? And the 400 means basically, or the 4xx errors means that the user did something wrong, but the user never did something wrong. Something wrong happened to your service, unless, of course, the error was from a validation, which naturally you would return the 400. But if it passed all that, because here it's an overly simplified example, but I show you that the validation is passed, and something went wrong with your service, then that should have been a 500 error. And actually, if you wanted to provide an even better experience, I would even tell you that, hey, the return, like you could structure your application such that you always return a 200 or 201, and then something might go wrong in your service, but as long as you have mechanisms in place, for example, you might be recording the request, right? You can fix the bugs, you can make sure that your service now operates properly, and then you can replay the request, and then the result will be the same, exactly what the user actually saw, that is a 200 or a 201. So in other words, don't use wrong error codes to inform the user, since the user cannot do anything to actually fix the problem, which in this case is a broken service, right? It was not the request that was wrong, it was the service that went wrong. So they should be informed appropriately. Lastly, looking at graphical user interface, how about using incorrect icons to signify some actions, right? This is prone to happen a lot in mobile designs, where we make heavy use of icons or symbols because we don't have that much screen real estate. So we will use a symbol, and this will mean some action. And if we use the wrong symbol for that action, imagine the surprises a user will get. All right. You get the issues. What can you do? What is something that you can do about that? Well, naming matters. You might also have noticed that feedback to your pull requests from more senior engineers always has some focus in naming. And yes, I know, as engineers, we can solve almost any complex problem, but we find tremendous difficulty in naming things. But at least we should try, right? At the very minimum, a good name should describe everything about what a function is doing. If multiple things are happening, put all of them in the name. And yes, I know you will end up with a huge name like get or create or something user. But this will actually immediately trigger your brain to start thinking, wait a minute, this name is too long, but it does describe the function accurately. Could it be that my function is doing too much, right? And then you end up with a better design. A good name also reduces need for documentation. And that's because seeing good names allows an engineer to easily skim through the code, selectively skip or deep dive in methods as needed. As a result, it reduces the needed documentation to the one that describes all the high-level concepts, such as, for example, system context diagrams or process diagrams. We can always understand what the code block is doing if we deep dive into it, right? But there is no hope to understand what that code block is doing to the whole system if we don't know how it connects to the bigger picture. That's why the high-level documentation is always very important. Next, be explicit about what is happening. Such is the role of explicitness. For example, don't change the updated date. And implicitly use that to infer, for example, that a product has been viewed, right? You might understand this and remember it for now, but your team members might not, or you, even over time, you will forget about it. Try to make all effects and side effects explicit in the code. If the functionality is implicit, how do you protect the feature? The feature when the functionality is accidentally removed due to a refactor or a new feature. And then, don't talk to strangers because stranger things happen, right? Use the law of Demeter. Trust me, it's not me, but the law is very, very simple. Avoid hidden dependencies. For example, while coding a class method, you should only invoke the methods of that class, the methods of the objects that you got as parameters, or the methods of the objects that you are creating in that method, in that code block. Direct call of functions from different classes or different modules, for example, how facade pattern is doing, are all hidden dependencies which you cannot easily manage. And of course, will lead to unexpected surprises. This principle, of course, holds true for functions as well, with the difference that you can invoke methods of the class there because functions don't have any class. All right. We learned quite a few principles today, but those are not the only ones, of course, and there are so many others, and of course, I need to make an honorary reference to them, and also give you some links if you want to do some more reading. So if you're interested in further learning, check out Constantine's law about high cohesion and low coupling, and of course, the well-known solid principles. And bonus from me, think distributed first. But start centralized. So this comes from me and certainly does not tell you to go and create distributed big ball of maths. What I'm trying to tell you here is that when you start designing a system and you split it into services or modules or whatnot, try to think that every other external service or module or external to the module that you're designing, every other external collaborator you're trying to use or talk to, think that they are distributed somewhere in the network. Obviously, this will be in the same code base if you start centralized, but thinking that will just trigger your mind saying, do I really need to talk to that collaborator? Do I really need to, it will force you to start thinking the communication lines and where responsibilities should live, and also start making you use the information expert principle as well. All right. If you're interested in further reading, there are a few sources here for you to go read more about. Also, these are sources that I used to make this presentation. And with that, that's all, folks, right? We're done for today. Thank you for listening, and let's have another talk another time.